you. From Zhejiang University and PhD from IEEE University. His research is on demand mobility services, big data analytics, multimodal systems optimization, pricing, etc. He's published more than 50 journal articles in top-tier journals, and he is ranked as among the top 2% of scientists in science and logistics area, and serves on the editorial board of DR Part C, Part E, and Travel Behavior and Society. And so today he's going to talk about his work on the large-scale simulation platform. So we'll get to it.
Okay. Okay. Thank you, Joseph, for the invitation. Yeah. So it's my great pleasure to be here to share some of my recent research with you. So today I'm going to introduce a simulation platform developed by my team and some AI-driven optimization algorithms for on-demand ride service operations. First of all, let me give you some background information and the motivation of this study. So we all know that the shared mobility market is increasing significantly over the past 10 years. For example, Uber is now serving around 26 million trips every day, operating in more than 70 countries and more than 10,000 cities. And Didi is the largest ride-hailing company in China. Is now serving around 30 million trips per day in China alone. And there are also other platforms like Lyft, Grab. Grab is popular in Southeast Asia. All is a popular platform in Middle East. Yeah. So this is quite a big market. Although these companies have achieved great success in their business, they still face many challenges, and there's many interesting research questions here. For example, from the perspective of the platform, they need to operate the system, right? So they have questions like how can we estimate passenger demand? How can we predict the driver supply, etc.? And how can we manage the drivers with passengers in the real time? And how can we set the price for passengers? How can we set the wage structure for drivers? And when we find some idle vehicles, how can we relocate the idle vehicles from one place to another so that we can mitigate the supply and demand imbalance across the space and across the time? And from the perspective of the government, they are interested in how can we impose or investigate the social impacts of ride-hailing services on traffic congestion and public transit usage, and how can they design appropriate regulations to enhance the total social welfare? So like in New York, there are some regulations for ride-hailing services, right? Daniel has some papers in this area. Yeah. So basically, the ride-hailing system is like a two-sided market with a platform in the middle and passengers and drivers on both sides. So in the demand side, the platform can set a price for passengers. So when the price is higher, then fewer people are willing to use the ride-hailing services. Another factor is waiting time. If you expect longer waiting time, the willingness to use ride-hailing services will be lower, right? On the supply side, the wage structure will affect the driver supply. And also the vehicle utilization rate will also affect the driver supply. Why? So imagine that if like 80% of the taxi time is spent on carrying the passengers, so they will have higher income, expected income over a day. But if the utilization rate drop to like 10% or 20%, they earn less money over a day. Even though the wage per order is high, it's still a little. Right? So the vehicles utilization is another important factor. On the other hand, the platform can control the on-demand matching strategies that can match the drivers with passengers. These strategies will affect the waiting time and indirectly affect the passenger demand. And on the supply side, it will affect the driver's vehicles utilization and finally affect the driver supply. And the more complex thing is that the passenger demand will also affect the vehicle utilization and indirectly affect the driver supply. And in turn, the driver supply will affect the waiting time of passengers and indirectly affect the passenger demand. So you can imagine how complex this system is. And the platform need to make a balance, need to appropriately adjust the price, wage, and on-demand matching strategies so that they can achieve some objectives. For example, to improve the system throughput, improve the platform profit, or enhance the social welfare, etc. So they may consider multiple objectives. But if the government does not have any control, then of course the platform will pursue their own profits. They don't care about the passengers, drivers, don't care about their benefits. So the role of the government here is to impose some regulations on the platforms so that the platforms may be incentivized or even forced to change their decisions. Like they cannot set the too low wage, they cannot use too aggressive price, they cannot have a too large vehicle fleet size, etc. So these regulations will affect the platform's decisions and finally force this platform to care more about the social welfare instead of pursuing only their own profit. Yeah. So this is a basic structure of the ride-hailing system. So today I'm majorly focused on the matching part, the on-demand matching part. Though I've had some papers related to pricing and waging, but today I'm going to introduce majorly the matching part. So talking about the matching mechanisms, there are majorly two modes. The first one is the broadcasting mode. That means when the platform receives some passenger requests, it will broadcast to the nearby taxi drivers. And each taxi driver has the freedom to pick an order from the list. So this is quite a common practice in Hong Kong. So in Hong Kong, the market is still dominated by taxi drivers instead of ride-hailing vehicles. So up to now, the ride-hailing services by private cars is still illegal. But the government tried to legalize this kind of services. But currently, it's still illegal. So the market is majorly dominated by taxi drivers. This is quite different from New York, and from many mainland China cities. So the taxi drivers will prefer this broadcasting mode. Why? Because they can also pick the drivers on the street, right? So they want to have more freedom. So they will prefer this broadcasting mode. But for the ride-hailing services majorly based on private cars, the dispatching mode is more popular. So in mainland China, like platforms like Didi use this dispatch mode for their drivers. That means when the platform receives some orders, they directly assign to specific drivers. And usually these drivers do not have freedom to reject the assignment. They may have a certain amount of freedoms, like they can reject at most three orders a day. Otherwise, they will get very high penalty. So that's the rules for Didi. But different companies may have different rules. But no matter how they define the rules, this is a kind of dispatch mode. But they may have different flexibility. Yeah. So you can see the difference between the broadcasting mode and dispatching mode, right? So from a system perspective, the dispatching mode will be more efficient because it's a centralized optimization, right? But for the broadcasting mode, the drivers have more freedom. So there are some pros and cons. So there are many challenging operational problems for both the broadcasting mode and dispatching mode. Take the broadcasting mode, for example. There is one key decision variable that is the matching radius. So imagine that if you have a larger matching radius, then the drivers and passengers can be matched more quickly. Yeah, this is natural because the drivers can see more passengers, so they can pick the orders, right? They can see the passenger requests quickly, and then they can answer they can pick the orders and go to pick up those passengers. But there are also cons. The cons is that the order will be broadcasted to every driver within a radius. So you cannot guarantee that the driver that is closest to the passenger will eventually pick the order, because the mechanism is based on first come, first serve principle. If a driver who is far away from the passenger is the first to answer the right, then he may get the order. Then the system may lose some efficiency because we always want the nearest driver we can pick the passenger, right? But in the broadcasting mode, if you set a too large radius, sometimes there are some faraway drivers get the order. So this is not efficient. So we need to determine some appropriate matching radius so that you can balance these trade-offs and try to maximize the system efficiency. So this is for broadcasting mode. For the dispatching mode, usually we need to solve a bipartite matching algorithms here. Like you have a group of passengers and group of drivers in different locations, and then you can calculate some measurements like their pickup distance, the value of the orders, etc. Then based on different criterions, you can solve a bipartite matching algorithms to pair the drivers with passengers, pair matching here. So basically, you need to solve an optimization problem in quite a short time. You need to solve it within 1 second or 2 seconds. You need to make decision quite fast. Yep. So this is for the dispatching mode. We will go back to dispatching mode later on. Another problem is the idle taxi repositioning. So we find that a large proportion of taxi time is spent on idle cruising, like even more than 15% spent on idle cruising. This will lead to a waste of taxi resources and also contribute to the traffic congestion. So why we have that? The major reason is that the taxi drivers or ride-hailing drivers do not have enough information of where they can easily receive the next passenger orders. So how can we solve this problem? So for human drivers, we can recommend some idle cruising routes for them. If they follow these routes, they have a higher probability of getting the next order. Or we can display some heat maps showing the real-time supply and demand information in different regions so that the drivers can make smarter decisions. But now we have robot taxis, right? So you can directly control the vehicles to search an optimal cruising routes. So talking about the on-demand matching, there are two difficulties. First of all, as I just mentioned, you need to solve the problem. Okay. You need to solve the problem very quickly, like within 1 second or 2 seconds. Secondly, you need to consider the spatial temporal demand and supply distributions, which may affect your matching decisions. So one point is that the system is quite stochastic, dynamic, and complex. The second point is that you need to solve the optimization problem very quickly. So how can we balance this trade-off? So we need to propose some efficient strategies. So overall, the taxi system or ride-hailing system is a very complex, dynamic, and stochastic system. So if you just apply some static optimization models, it may not be good enough to design some very good real-time operating strategies. So we are thinking that how can we utilize AI? How can we combine the AI with optimization to solve these kind of problems so that we can learn from the real-time data, and finally we can dynamically adjust our operating strategies. However, if you want to train or test an AI algorithms, you need a test bed. For example, if you want to train AI for video game, you need a video game, right? But the problem for the ride-hailing system is that the ride-hailing companies cannot take the risks to test some immature strategies, right? You cannot like train some immature operating strategy in their system. They will not allow you to do so. So we are thinking that how about we establish some simulation platform that can replicate the dynamics in a real system, so that we can use the simulation platform as a testbed for the training and testing. Even though we use non-AI optimization models, we still want to test different optimization models and pick the best one before we actually apply the models to the real system. So that's the motivation of our study. So we are going to establish a simulation platform that can replicate the dynamics of the real taxi or ride-hailing market. So next, I'm going to introduce some details about the simulation platform. First of all, it's operating in a real transportation network. So usually we use OSM because it is open source. But if you have more detailed maps, like you buy some maps from Google Map, it's also okay. You should plug the network into our simulator, and then it can still run. Okay. And we can track the dynamic movements of the vehicles, check their detailed trajectories, passing in each intersection, each road link, road segment, etc. It has 4 major modules: the pricing module, matching module, repositioning module, and routing module. Let me introduce them one by one to you. First of all, in terms of the matching module, as I just mentioned, we have broadcasting mode and dispatching mode, right? So we designed some basic algorithms for the broadcasting mode and dispatching mode. But the users, later I will show you the code, you can download it. If you use it, you can replace this module with your own algorithms. You can have your own dispatching algorithms, and then you can test the performance. And regarding the routing module, we make it simple. We just calculate the shortest path over the OpenStreetMap. So if you consider conjunction, then you can update the weights. For each link there is a weight. So originally it's the travel distance, right? Then you can update it to the travel time. Then you can consider the traffic congestion because the speed on different links may be different, right? So this is a routing module. It's somehow fixed. And for the pricing module, our objective is to estimate passengers' willingness to pay. That means at what price they are willing to take a taxi or use a ride-hailing service. Okay. So for this part, we conduct some survey so that we can estimate this kind of parameters. And for the repositioning module, that means when your vehicles are idle, how can you control the vehicles move from one place to another? So we have some basic algorithms like the random walk and some basic behavior models. But you can design your own optimization models to guide the vehicles to do the best idle cruising. Okay, so you can try to maximize the system performance by designing some algorithms here. So generally speaking, this simulation problem is quite complex. You can modify matching, pricing, repositioning here. Routing is more fixed, so we do not need to modify it. Yeah. There are some more details here. Just not go to the details. I just want to mention this agent-based system. That means each driver and each passenger is an agent with its own properties and some own behaviors. Like different passengers may have different tolerance of the waiting time, tolerance of the maximum price, etc. So about the data, we have some open source data. Yeah. So first one is New York City data. I think New York City is most successful in open source this kind of data. Yeah. Everyone use it. Yeah. So in our published version of the code, we also use the NYC data. But there are also other possible data set. For example, Didi also partially published their data set. In 1918 or 2019, 2019, it's 2019. They published some kind of data, right? Then you also got data? No, not yet. Not yet. Okay. Yeah. They publish data in some website, Chinese website. But something happens to DD. Yeah. There's some political problem. You don't know the story, right? Yeah. I can tell you. Yeah. Because DD wanted to get listed in Nasdaq in United States, but they have some private information, right? Like the maps, passenger information, etc. Yeah, but they need to move some of this data to the U.S. government, right? So the Chinese government stopping it. Yeah, so the Chinese government wanted to stop it, but in a national celebration, the Chinese government was busy with the celebration. They don't know, but on that day, Didi got listed in Nasdaq. Yeah, and the president was quite angry. So they later on the government imposed very heavily regulations on Didi in China. So the market share of Didi was more than 90%, before 2019. But now it's 70%. Yeah, it dropped from 90% to 70%, even 60%. Yeah. So after that, Didi closed all this data. They don't open source this data. Yeah. So it's quite sensitive. But it was open source, right? So many people still have this data set. Yeah, I still have this data set. So I use this data set also to do some calibration. So in two cities, one is Chengdu, one is Haikou. If you see some papers in TR policy, you can see some data, right? DD data in Chengdu and Haikou. Yeah. That's the story. Okay. Yeah. Anyways, back to my research. And we also have some private data sets in Hong Kong. But this data set are totally private, so we don't publish them. We majorly use this kind of data set to do some projects. And as I mentioned, we also conduct some surveys. For this part, we already open source it in our code. I will show you the link later. Yeah. So these are the distribution of the questionnaire survey. Like if you try to measure the willingness to wait of passengers during the matching stage, it looks like a normal distribution. Like most of people are willing to wait for almost 4 minutes here, something like that. And also we have the distribution for the willingness to wait during the pickup stage, and also the willingness to pay, like at what price you are willing to take a Uber, take a taxi. So these are the distribution. You can put this distribution onto the simulation platform. So these are basically some parameters. Okay, then we have a demo for our simulation platform. This is the code. So you should go to HKU Smart Mobility Lab. Then you can see the open source code. So this is a demo. We use different color to represent different status of the vehicles. Like the yellow color represent that they are idle cruising, and the red color means they are carrying the passengers. Green color means they are on the way to pick up passengers, etc. And we also do some validation based on the Hong Kong data set. So I would say most of the data set only have the OD data, don't have the taxi trajectory, right? But fortunately, in Hong Kong, we collected some private data with a taxi trajectory so that we can do some validation. So because in our simulation platform, you put into the OD, then you get the trajectory of those taxis or ride-hailing vehicles, right? Then you can compare the actual trajectory of the taxis with the simulated one, right? Then you can measure the utilization rate, etc. And finally, you can make the comparison. And we find that average is around 12%. We think it's acceptable. So that's for the simulation platform. Later on, I'm going to introduce a few studies, briefly mention a few studies based on this simulation platform. Yeah.
So as far as the sort of background tracking information.
Yeah.
So you also have that data to sort of calibrate the sort of speeds, driver speeds.
Yeah. In Hong Kong, the answer is partially yes. We have some kind of survey data and have some traffic flow data on the strategic roads, but not for every roads. So we need to have some inference for those minor roads. Yeah. So then we can have that kind of background traffic. Yeah.
And then follow, because you mentioned, okay, we could plug in our own sort of maps.
Yeah.
So how does that then influence that sort of speed input, right? Because those maps have different sort of layout, right?
Yeah. So in the open, that's why in the open source version, we don't have the speed module. We take it out, right? Don't have speed module. It will just give you a parameter, you set a constant speed, right? But for our own project and our research, we have that speed module. Because it's big complex, because in the map, for each link, you need to know the capacity, right? You know how many lanes you have, what is the length, right? And then you need to calculate the number of taxis and number of background traffic. That's the density, right? And then you have density, capacity, then using some traffic flow model, then you can calculate the speed. That's how we do in our project. Yeah. But it's not very standardized, right? If you get some map, then you may lack the information of capacity or any other factors. So you cannot do that, right? So we in the open source version make it simpler. Yeah, just a constant speed. Yeah. Okay.
Another question. So for the calibration, you're modifying the speeds to calibrate it?
No. So the blue curve are the actual trajectory data. So for the taxi trajectory, it has different status. It can be occupied, it can be idle, right? So for each hour, you can calculate the vehicle utilization rate. That means how many vehicles are occupied, like 10% or 20%, right? Like here, this 30%, right? So this blue data are the ground truth data in different weeks. Yeah. This red one is the utilization rate simulated by our simulation platform.
Right.
Yeah. Because in our simulation platform, what we give to the simulation platform just the OD information of passengers. Right? Only the trip information. We don't give the taxi trajectory in. They simulate the taxi trajectory with their status, like idle, occupied, etc. So you can also calculate the utilization rate over different hours. Right? Then you can make comparison.
Are there like parameters that you're adjusting to try to fit it better to the? Are there parameters that you're adjusting?
Yeah. There are. Let me think. Like speed. Speed is a parameter, right? If you keep it a fixed speed, it's a parameter. And also, you can say those passengers' willingness to wait and willingness to pay are also parameters. But we just do it by questionnaire survey. Right?
So some of them you find other sources to get the numbers of for.
Yeah. You can have your own distribution. But for us, we conduct we send out 1,000 questionnaire survey, and then we do some kind of calibration, right? You cannot say this always true, right? Because it depends on the region, right? And also it depends on the number of vehicles in a city. But in Hong Kong, it's easier because the number of taxi licenses is fixed. It's 18,000 fixed. It has been fixed for 20 years. So this is easier. But for for other places, you also need to get the total number of vehicles. Yeah, this is another parameter. Yeah.
So the fleet size you're running is 18,000 vehicles?
Yeah, 18,000. Yeah. Yeah. So next, I'm going to introduce quickly introduce a few of my research related to this simulation platform, or using this simulation platform, right? The first one is the broadcasting strategy design. As I just mentioned, how can you set the broadcasting radius? Should it be 1 kilometer, or 3 kilometer, or 5 kilometer, right? How can we determine? Then first of all, we conducted some initial studies. We first define a few metrics like the vehicle utilization rate, the passenger waiting time, pickup time, etc. Right? Then we give different weights to these objectives, and then we have some kind of a weighted sum of these objectives. So we have a total system performance, which is a weighted sum of these objectives, and then based on this criterion, we're trying to find out what is the best matching radius in different regions and different time slots. And we find that it varied across the time and across the space, very significantly. Yeah. So in different regions, in different time slots, the optimal radius could be quite different. Okay. So this motivated us to develop some strategies that can adjust the optimal matching radius based on the location and time slot. So our objective is to determine the optimal time slot, right? For this problem, because the system dynamics are quite complicated, it's hard for us to model them into a mixed integer programming problem. So we do it in another way. We try to predict. We turn it into a shipwise learning problem. That means we try to predict the system performance given different matching radius. And then in the inference stage, we can try different matching radius and then pick the best one. So that's our idea. So first of all, we need to generate some data. So we have a simulation platform here, right? So we can try different matching radius. Like you try matching radius equal to 1 kilometer or 10 kilometer, and you can change it, randomly change it. Okay, so for each matching radius, and based on the current supply and demand information and spatial temporal features, you can get some system outputs, like the order fulfillment rate, driver utilization rate, average pickup time, waiting time, etc. So you have so many system performance metrics. Then you can construct the features and labels. These system performance metrics are the labels you're going to predict. And these are the features. Features, we have two types. One is some objective things, like the current supply and demand information, or the spatial temporal features. This can be observed from the simulation platform or from the real system. These are objective information. Another part is the decision variables. That's the matching radius. Like if you change the matching radius, you can have different system output, right? Like if you set it as 1 kilometer, you get this group. You can set it as 3 kilometer, you get another group, right? So we use this as feature, use this as labels, and then we try to train a shipwise learning model. It's actually a multitask learning model based on a transformer structure. Why we use multitask learning? Because we have multiple objectives. Then finally, after we train this model, then we can do the inference. So when we try to apply this model, how we do it? First of all, based on the current batch, you can observe some demand supply information and some spatial temporal features, like the location, time, etc. And then you can try different matching radius. Like you set matching radius from 1 kilometer to 10 kilometer, and each time you add 1 kilometer. Then for each specific matching radius, you can get a group of system performance matrix. Then you can draw some curve like this, right? Then you can pick the best matching radius. So because the inference speed is quite fast, if you run machine learning model, you can find that the training is quite time consuming, but if you go to inference, it's quite fast, right? You can just output the results within quite a short time. So you can try different matching radius and then pick the best one. So this is the basic idea. And there are some details about the prediction model. I just skip this part. And these algorithms. So these are results. Results show that our proposed method can achieve better performance than the baselines. Okay. So this simulation, these experiments are run on the simulation we mentioned before. Yeah. The second research is about the, sorry.
So, you understand correctly, so you basically optimize the performance measure in each region.
Yeah.
So it's not a global, because so are vehicles allowed to move between regions?
Yeah. Good point. Yeah.
But but are you looking to then have like, okay, I'm gonna optimize the radii, but to maximize the global?
Yeah. We did not consider this factor here. Yeah. This good point. So it's okay to consider. You need to have some structure to capture the global information so that you can some kind of coordinate the optimal matching radius in different regions. Right. Yeah. This can be an extended study. Yeah.
Because it seems, I don't know, it would seem a bit easier, right? Because then you just have one objective, right?
Yeah.
Or learning.
Yeah.
Or not so much. I don't know.
Because we have the complexity here is we have multiple objectives. You have like different indicators. Some on the vehicle side you have the vehicle utilization. On the passenger side you have the waiting time, etc. So does this study majorly focus on the multitask part? Yeah. But we neglect the combination of global optimization and localized optimization. Yeah.
So which radius was the best radius then?
It depends on the region and the time slot. Yeah. So you can imagine in some when in some peak hour and some BC area, like in Wall Street, right? You should set the matching radius very small, right? Because so you can find a passenger driver very easily, right? But if you go to some suburban area, you need to set a very large matching radius. It could be different. Yeah. So the second study is about the dispatching. As I just mentioned, for dispatching, you need to solve some bipartite matching algorithms. You have a group of passengers, group of drivers, and try to match them, determine the pair-by-pair matching between these passengers and drivers. But if we use some classical bipartite matching algorithms like the KM algorithms, they are myopic. That means they only looks at the current batch of passengers and drivers. They don't care about the future. However, this system is a sequential system. That means your current matching strategies, current decisions will affect future supply and demand distribution and will further affect your future decision makings. So there is interactive connections between the matching strategies and the environment in terms of the supply and demand dynamics. So we can model this kind of system based on the macro decision process, and then we can solve it by reinforcement learning model. However, there's a problem here. That is, you also need to solve the optimization model very quickly in real time. So when you do the online optimization, you still need a very simple model, right? You cannot have a very complex model. So here our solution is to modify the weights of these bipattern matching algorithms by adding some future values. We don't change the optimization algorithm here. We still use KEM algorithms, Hungarian algorithms, etc. Classical one, but we change the weights. For example, the original weights is the trip fare of this order or the pickup distance, etc. But now we add a future value here. Then how can we get the future value? And what is the meaning of this future value? First of all, we train these future values based on offline learning, offline reinforcement learning algorithms based on our simulation platform. That means we train our reinforcement learning model based on the simulation platform. Then we can get some state action future values. Then for each location, for each time slot, we get some. We can infer some future values. This future value can represent the expected revenue of this driver after dropping off this specific passenger. So that's the physical meaning. Let's see one example. For example, if we use a standardized bipattern matching, then for these 3 passengers, if you just have 2 taxis, so it is better for you to pick up to serve the first and second passengers because they have higher instant rewards. They have this is a longer trip. It's $50. This is $30. So it's better for you to serve these 2 people, right? But if you add the future value, you may change your decision. For example, for the second passenger, maybe his destination is quite far away from the city, right? So if you finish the trip of the second passenger, you cannot find the second passenger, right? So this is not good for the taxi driver. But for the third for the third passenger, its destination is a railway station. You can easily get the next passenger, so it may have a higher future value, right? So your best decision could be serve the first and the third passenger, right? So this is just a very simple example to illustrate how the future value can affect our decisions. Then the final question is, how can we determine these future values? So this is the reinforcement learning part. First of all, we need to define a macro decision process. We should define the action, state, reward, etc. So generally speaking, the reward is designed as the overall revenue of drivers over a day. When you have ride pooling, then you also need to consider the routing costs. And if you want to consider passengers waiting time, you can also consider. So you have different ways to define the reward structure. But generally speaking, you need to define the reward as the benefits over a day, not just for 1 hour or 1 batch, right? So this can incentivize the agents or the reinforcement learning algorithms to try to maximize the long-term reward instead of focusing on just 1 batch. Okay, so this is the basic idea. Then we train some reinforcement learning algorithms like the actor creating network to solve this MDP. Nowadays, you know, the AI have been developing quite fast. We now have better algorithms, much better algorithms than the actor creating structure. So now I hear that there's some algorithm called a decision transformer, which is quite nice. Yeah, my students are testing this kind of algorithms based on some DD's data. Yeah, the performance is quite good. Yeah. Anyways, finally we can get some. Yeah.
Component here.
Yeah. Yeah. The idea is that the critic network. Actor creating network. The idea of actor creating network is that it has 2 new networks. One is the actor network, which can make actions based on the state it perceives. So it perceives the state and make the action. So this is like a student. And this quick network is like a teacher. So its on purpose is to evaluate whether the action made by this actor network is good or not, right? So the actor network is like a student to make some decisions, and this quick network is like a teacher to give some evaluation. Yeah. So this is the basic idea. So we train these two networks simultaneously. So finally, after we train the actor network, then we can just use the actor network to output the actions. That's the basic idea. So finally, we get some spatial temporal value function maps like this. Like this is the CBD area, right? So if your chips have the destination going to this CBD area, then they have a higher future value, right? Because it's easier for them to get the next chip. And the algorithm can even implicitly consider the traffic congestion. For example, in this region, in the very core center here, because there is a severe traffic congestion. If your destination go to this region, you may get stuck here by the traffic jams, right? So this is not good for you to maximize the revenue over a day, right? It becomes some cool areas here, right? So all these future value functions are automatically learned by the reinforcement learning algorithms. We don't have any rules for them. We just let them to learn by themselves. Yeah. And we also conduct some experiments based on our simulation platform and find that these algorithms have good performance. Next, the third research is about the idle vehicle repositioning. So this is a very classical problem. Researchers have investigated this problem for quite a long time. But recently we have a paper which has a new idea about this vehicle repositioning task. So we see one problem for the reinforcement learning. If you want to do some large-scale optimization, or you want to have some realistic idle cruising route. For example, if you want to recommend some idle cruising route for a driver, you need to have a specific route, right? Like you follow this route and go, right? But if you use reinforcement learning, the problem is that for each link, you need to give it a state, right? So in Manhattan area, how many links you can have? Maybe more than 10,000, right? That's quite a large number, right? And you also have many time stops. So
may I have your attention, please? May I have your attention, please? This is your Fire Life Safety Director. Please be advised, we are currently conducting testing of the fire alarm system at this time. Please disregard all alarms. Once again, we are conducting testing of the fire alarm system at this time. Please disregard all alarms you may hear. Thank you.
Good. This is important. Yeah, you know the big fire in Hong Kong? Yeah, that's tragedy, right? Yeah. It's very important. So if you assign every state to every link, it makes the training of the reinforcement learning quite complex, right? So we are thinking that how about we separate the tasks into two steps. In the first step, we just make decisions on a high level. For example, in New York City, in Manhattan area, we have 62 or 63 zip codes, right? So we only determine which region or which zip code we are going to, right? For example, if you are here, then we determine this region is the best location for you. Then just go there. After we reach that specific region, then we go to the second step. Then we call a Monte Carlo tree search for generating a specific route for you. Okay, so that's the basic idea. And we conduct some experiments based on our simulation platform, and we find that if we combine these two steps together, we can make better performance than only using the reinforcement learning model or only using the Monte Carlo tree search. And we also have some research about the ride pooling operation. For ride pooling operation is more complicated. So this problem is quite complicated. Why? Because every time you need to determine whether you are going to pair these two orders together in one trip for this specific vehicle, you need to solve a VRP, vehicle routing problem here, right? Or TSP, right? So it's quite time consuming. If you do OR, you know it, right? It's NP hard, right? And you have thousands of vehicles, thousands of passengers. So you need to solve this VRP thousands of times in one batch, right? This is nearly impossible. We use Groovy to run this problem. Even if we just have like 20 vehicles, 100 orders, it takes a few hours, right? So it's too slow. So we are thinking that whether we can combine the optimization models with the AI models so that we can speed up the process. So the general idea here is to use the machine learning model to predict the VRP results. So what is the meaning? Because your matching decision is based on these VRP results. Based on VRP, you can estimate the detour, the routing length or the detour of passengers, something like that, right? And then you incorporate it into one single mixed integer programming problem. It's quite complicated, right? So we separate it into two stages. In the first stage, for each possible VRP, we don't solve it. We use a predictor to predict the routing distance. That's it. And then for this specific route, we just can predict. Predict does not have takes any time, right? Then predict, and then we solve the matching problem. Then this first stage done, and then go to the second stage. For each specific route, we just solve this single VRP because now we know the matching. We know this guy is going to pick order A and order B, right? We just need to solve this very simple VRP, right? Just two order and one vehicle. And no matter how many vehicles you have, you can solve it in parallel, right? You don't need to mix them together, solve them together. You can separate them. So that's the major idea. And there's details about the algorithms. Don't go to the details. Here I'm just going to show you that compared to Groovy, we can increase the computational speed by more than 1,000 times, so that we can make it possible. We can solve this problem in a reasonable time. Like we can, for 15 vehicles and 200 orders, we can solve it like within 10 seconds, and that's already acceptable for the ride pooling operations. Yeah. And the last research is about the combination of ride-hailing services and public transit services. So the idea is that we try to use the ride-hailing services to address the first mile or last mile issues for people using public transit. That means they can first take the ride-hailing services to some public transit station and then use the public transit station to go to their destination. Or first use public transit service, and for the last mile, they use ride-hailing services. So they may achieve a win-win situation. On one hand, the passenger can reduce their costs, right? They can save some money. If they take the direct trips, it's quite expensive. But if they just take the taxi to a very convenient transit station and then take the metro to the destination, it could be cheaper. And secondly, the vehicles also have the possibility of having higher utilization rate. Why? Because they can sometimes stay in some specific region. For example, one taxi can serve for one specific transportation hubs. Just take the passengers to that transportation hub and then take another passenger to that transportation hub. They just focus on that area. This can somehow increase their utilization rate and reduce the idle cruising time. So there is a possibility to having a win-win situation. Then we design some reinforcement learning model to do this task, to recommend some routes for multimodal route for passengers and simultaneously dispatch the passenger, the drivers, taxi drivers to serve these passengers. And we also conduct some experiments in New York City, Manhattan area. And we find that the performance is good. Okay. Just skip this part. And finally, let me briefly mention some applications of our research. First of all, fortunately, we have a partner in Hong Kong, a local taxi companies, actually second largest taxi companies in Hong Kong, with around 1,000 taxis. So originally, they don't have any algorithms. They are like they receive some phone calls from the passengers and then do the matching manually. Some kind to do the matching. So we see there's an opportunity here. So we design a whole matching system for them and then use it that completely use our system. Yeah, and we find that we can increase their driver revenues by around more than 5%. Yeah. So and secondly, we have an app for the taxi drivers, which is called the Idle Cruising Recommendation app. So in Hong Kong, the taxi drivers like to stay in the taxi station to wait for the next passengers. So we will recommend the best nearby taxi stations for them. So if they go to these taxi stations, they can have higher probability of getting the next order. And we also apply our algorithms in Shenzhen. We have a collaboration with the Shenzhen bus company, which control 10,000 taxis. It is a bus company, but it also has lots of taxis. So we also test our algorithms based on their system. And they say that the driver's income can also be raised by about 5%. So finally, talking about the future extensions. First of all, we are now developing a multimodal traffic simulation platform. We try to incorporate metro bus services, even some emerging modes like drones, etc., into a comprehensive multimodal traffic simulation platform. So we are doing this, and we try to open source it in 1 or 2 years, because it takes a long time to write the code. And secondly, we haven't explored this area, but we think that this simulation platform can also be extended for other possible scenarios like the last mile delivery, food delivery services, etc. There are some similar problems like matching problem, pricing problem, etc. And this simulation platform can also be used for carbon emission calculation, because if you can accurately measure the traffic flow, traffic density, etc., you can do the carbon emission estimation. At least you can estimate. So these are some relevant papers to this series of studies. First paper is about the broadcasting mode. The second paper is about the simulation platform. So if you want to know the details of the simulation platform, you can check the second one. Third paper is about the coordination of ride-hailing services and public transit services. That's a research file in our slides. The last one is about the idle vehicle repositioning problem. We propose a mean field Markov decision process for idle cruising. Okay, that's all for my talk. Thank you. Yeah, please.
Laws for taxis or ride-hailing in Hong Kong?
Idle, yeah, yes.
Yeah, are there laws, are there laws restricting certain idle times or not specific zones because there are.
I based on our data, we find that it's around 40 to 60%. In Africa, it can even raise to 60%. Yeah.
A couple comments.
Yeah.
Very relevant research to what our lab's doing too. Your research on the last mile, you commented that when the taxis end up circulating around the hub, they become more, the utilization rate goes up. We actually did do a study that published in 2019 where we looked at, we didn't look at Manhattan, so we looked at Long Island Railroad because that there's more opportunity there to look at last mile access. Because it goes all the way out to Long Island. And we saw that the effective capacity increase by relying on LIRR or dropping people off at that location as a hub increases the ride pooling operations 5 times.
Yes.
And then you also had you talked about integrating AI into dispatch for the ride pooling. So you compared against Groby. Did you compare against just simpler tour construction heuristics?
We also compare with some heuristics. But the reverse raised this question. So we will.
There have been some studies, I think from researchers in Montreal that showed that it's pretty comparable. It doesn't even those simple tour construction heuristics, 2-op, K-op, insertion heuristics, they're pretty effective. Especially once you break it down, if you're operating this in online operation, you were saying the routing problem is complex, but if once you've assigned it, it's pretty small, right? It's a couple of passengers, so the problem itself is actually
exactly. So our paper is a kind of heuristic, right? Because the first stage you need to separate, right? Separate the problem, right? And we just use the machine learning to predict the VRP part.
But that takes there's a training period for that.
We need to generate many VRP examples, samples, right? Even millions of the at least thousands of the samples.
You're basically then you have learning model to represent the solutions.
Yes.
And for the repositioning, did you consider combining that with the dispatch?
Oh, great point. We will have considered. The point is that we see some other papers who already solved this problem. They combine. Oh, you have one. Oh, maybe it's your paper. I remember I saw some paper. I combined the dispatching with repositioning. So we didn't do this paper. So the idea is that the reposition can be a point in the bipartite matching, right? It can be a virtual point, right?
It seems to play a very significant role in the performance. Once you add in.
You just think that there are some virtual passages, right? Okay, thank you. Please.
Actually, I have one question. So you mentioned you use the machine learning for prediction. So how do you make sure that the prediction satisfy the constraints?
The constraints. What kind of constraints?
So did you use the machine learning to predict or evaluate the ocean?
The point is that we only use the the machine learning to predict the VRP part. So actually, I don't show the equation, the optimization model here. So in the optimization model, you can see that it's a mixed integer. I think it's a quadratic programming problem. Mixed integer quadratic programming problem. Very complicated. Yeah, and in the constraints, there are many VRPs, and they are like coupling together. They couple together these VRPs, right? So our idea is first to do the decomposition. Like we just for all possible elimination. Like here we have A, B, C, 3 passages, and you have 2 vehicles, right? Then for this vehicle, one possibility is to pick up A and B, right? Another possibility is to pick up A and C, right? Another is to pick A, B, C all together, right? So you have many possibilities, right? So in the optimization, if you solve the single optimization problem, you need to mix all these things together. It's quite complicated, right? But here, our machine model is used here. For route A, B, we just use the machine model to predict the routing distance of picking order A and B. Okay. So we predict this routing distance, right? If it is A and C, we predict this route distance. Okay. And after we predict, then it becomes some parameter. So they are still in the constraint. They're still in the constraint, but the constraint becomes simpler. Right? Becomes simpler, right? You just have some machine learning generated parameters. So the problem is that you need to make sure that for this specific route A and B, whether you can predict it very accurately, right? So you need to generate many samples, and then you need to train a very good model to make the prediction. So our model can achieve over 90% accuracy. So it is really good for this problem. So because when you do the matching, you just need to have some rough estimate. You don't need to have a very accurate estimate. Just need to a rough estimate to help you to make decisions about the matching, right? So now you know if this vehicle take A and B using machine learning model, it travels like 10 kilometers, and you take A and C. Right? If you travel like 20 kilometers, so of course taking A and B will be better than taking A and C, right? So we just take this decision, right? So even though the accuracy is not 100%, so based on our experiments, you will not very significantly affect our optimal decisions, because you just need to have some rough estimate. You just know A and B is better than A and C. That's enough, right? Yeah. So that's the point. Yeah.
I think there's some literature on like the cluster and route kind of approaches where you assign first to vehicles and then you route them. That's kind of what
Yeah. There's also some
and so in your case you then turn the routing part into like parameters that so you're just looking at the clustering part.
Yeah.
Do you also consider so there's like continuous approximation methods?
Yeah. Good point.
That could be
Well, we actually use them as baselines. Yeah. So Carlos Staganzo developed many continuous approximation algorithms, right?
Quickly.
You can quickly. Yeah. So the machine learning model actually replace that part. Yeah. They can be more accurate. That's the point. Yeah. Any other questions? Okay. Thank you.